Okay, so the reaction that we're doing, I need a marker. Can you see the entire whiteboard from there, Landon?
Yeah.
Okay, so the reaction that we're doing, everybody, is we're going to take some hydrochloric acid. Okay, listen up here, please. Okay, so some HCl. So by the way, when you need your HCl, I'm just keeping it up front for safety. But this is your hydrochloric acid. You'll notice in the lab that it calls it 2M hydrochloric acid. Capital M stands for molarity. We'll actually learn more about that next time. For now, just know that it's the concentration of it. So like 2 molar is stronger than a 1 molar, but it's not as strong as a 12 molar. Safety-wise, we will put on lab goggles here in a second because hydrochloric acid in your eyes would be very, very bad. Okay, if you get hydrochloric acid on your skin today, just get it under the sink, wash it off. It will start to burn, but it's not going to get to your bone in like 10 seconds. So.
Just give it 15 minutes.
But I mean, it just will continue to burn if you don't get it out. Do be cautious though, if it gets on any clothing, you might find holes in your clothes tomorrow. There are lab aprons in the prep room if you want to wear one, if you're worried about it. Otherwise, just once again, it's not instant, like it's not like you drop it on your shirt and like a hole appears. It normally shows up like the next day you'll notice it, or like after you wash it or something. So, but do be cautious with the hydrochloric acid, that's the most dangerous thing. Okay? Okay, we're going to react our hydrochloric acid with magnesium metal. The magnesium metal is inside that little food cup. Okay, this is safe. You can touch magnesium with your hands. That's fine. One note of difference. The lab says to use 4.5 centimeters. We're going to use half that amount. So I've already cut it to about that size. You'll just measure and get accurate. Okay? But the reaction is the magnesium will react with the hydrochloric acid. And in result, it's going to kick off the hydrogen that's paired into hydrogen gas. So this is the gas side of our lab. And then leave behind this thing called magnesium chloride. Okay? So that's our basic reaction of what's happening. The goal of this lab is we're calculating what is known as the molar volume of a gas. In this case, hydrogen. The benefit of knowing the molar volume is it tells you how much gas you need to fill a space. So let's say we wanted to recreate the Hindenburg and fill a blimp with hydrogen.
That was a great idea.
Yeah, to repeat something that went really well. The molar volume helps you know how much gas is needed to fill it up. Okay, so that's what we're calculating. We'll then compare what you figured out to be to the true value of it and see if you did a good job in the lab or not. Okay? What other things do I need to tell you beforehand? The way that we're capturing our gas is known as a process as water displacement. So water will be in the tube. The gas will bubble up the tube and push the water out. Just to kind of give you an example when you start going, you're going to be making a little cage for your hydrogen gas with this piece of copper metal. The biggest thing is the cage has to be small enough to fit inside your ettimeter tube, but not so small that the bubbles can't react with it. So don't make it too tight, otherwise it will take forever. You can kind of look at the example cages around, some were created better than others. But if you create it too tight, the reaction goes really, really slow. So yeah, second period, reaction still bubbling, they're going to come stop by after fourth to check their measurement because it wasn't done. But hopefully since we're starting your guys now, hopefully it will be done before the bell comes. So, but the basic idea of the cage is I'd probably use your pencil. That seems to work the best, but the basic idea I'm going to show you with my finger is if you wrap it around, kind of create a little curly-Q thing, right? And then just kind of tighten it up, and then the magnesium will just fit right inside of that. But you got to test it and make sure that this can fit inside the tube. One other difference from what your lab says is the lab talks about, if you want to turn your lab to page 2, it has a basic setup for you. Okay? We aren't going to use a rubber stopper at the bottom of our tubes like this one shows, because I don't have any rubber stoppers that are small enough. So when you make your cage, it will work if you do it right. You're just going to make a little hook at the end to hold it on, so it doesn't fall out. If it falls out, then we'll have to act quickly and get it back in without messing things up too much. So that's all I'm going to say for now, and I'm going to let you read the procedure. But if you have questions after reading the procedure, don't hesitate to ask. But that's part of it, is you interpreting what these procedures are. So, anything else we changed? I think that's it. So go ahead and get started. Turn the procedure. Start with step number 1. And then once we all get our reactions bubbling, then we'll do some calculations while we do. Okay?
We're gonna fill up this beaker with water.
Isn't it supposed to be distilled water? I think that is distilled water.
No, it doesn't say distilled water. It just says water. That's a lot of distilled water.
And how much are we putting in the beaker?
3/4 full of water.
If it doesn't specify, then
Okay.
Little bit.
yeah, it will always tell you if it wants distilled water versus.
There we go.
Is this where we're putting the?
Does this look good?
Yeah.
Can we do that right now?
Yep.
Okay, so that's.
Oh, well, you can use,
Obtain
you
that
can probably use
is-
this to measure out how much.
Okay.
And then,
Obtain it.
is this a good enough cage? Well,
Measure and record a stat table the exact length of the magnesium ribbon.
You get it.
What is the exact?
Okay, so it doesn't fall out.
Oh, am I supposed to do this? Okay.
No, you can do it, yeah, I just left it up there, but yeah, you can pour it, just, you know, pour it on there.
Okay, are we measuring in centimeters? And there's 0.1 centimeter.
You need,
Wait, we need to record it to 0.1.
oh, yes.
Isn't that just a milliliter?
So that's about 2 centimeters. How long is it? Like 2 centimeters. Almost 2.
It's like 2.3.
Actually, it's bringing it to.
Oh, I would say 3. Yeah, 2.3.
It's about 2.3 centimeters.
Mass of milk.
It worked. I'm gonna drop this.
Gotta wait. Is this a little baby scale? Is it?
You know.
That was cool. Actually, I think it looks like it.
Yeah, we need to get it out.
It's a weird shape still. Okay. Really good. That was good. That was pretty good actually.
You were testing it, now you can't get it out.
Oh my god.
Did you get it?
Yeah, because mine is a snappy.
Okay, here's some in, we need it.
How much? Hydrogen fluoric acid gonna put in this? About 15 milliliters.
Oh, and then we put the number of centimeters on the bottom right here.
I'm filling this with hydrochloric acid.
So we would put, I don't know for sure, this is something I'm wrong, but would we put 2.3 on the bottom right here? Yes. Oh, no, hold on. It's for 1 centimeter. So we want to get it to grams, right? So what I think we do multiplied by this, because we want these to cancel out, right? So we multiply those. Yes, okay, I would do that. Oh, have a calculator? So it's 2
Wait, how do we get that?
What did you get for it?
It's .02.
Show them what you did.
I don't know what we did.
Okay.
I think I paid
So, what we did
It's
to
on the
find
calculator.
the mass of this little tiny piece of magnesium that's 2.3 centimeters is we multiplied 0.00806 grams by 2.3 centimeters because that's the amount of grams percent.
I can show
15
this to
milliliters.
visual aid.
Yes.
Hydrochloric acid.
Okay, so this was a ratio we were given. Is this ratio right here, and we want to get to grams because we're trying to find the mass. So we're going to put centimeters on top here, centimeters on bottom here, so they cancel. That way we end up with grams.
We already twisted up.
That's what we put in the calculator.
We have made our copper cage. Okay.
So place this magnesium into the copper bar cage. Does that fit in here?
I wonder if we get to use sulfuric acid.
You're putting all 15.
Someone like bring it up close. Do you want to like pick up the camera and like bring it up close? I don't know if it's gonna hold it though.
But that doesn't.
We're gonna do it slowly so they don't mix.
Ah, this is supposed to work.
That's why you got this side, 'cause that way it doesn't gravity doesn't
Yeah.
push it down.
Okay.
Okay, how we all do? Making a cage over here?
Yep. Don't be nervous, Carly.
Okay.
Slower?
Sorry, this is super boring.
Oh, it's okay.
This is.
Oh man, this is fun.
This is so fun. Okay. That's not gonna fit in the
Now,
Yeah.
insert wire into rubber stopper, but you just hook the end of the copper wire around it.
On the top.
Yeah.
How are we doing?
Oh no.
Trial and error.
Yes, guys.
You don't want any bubbles.
Where's the 15 milliliters on that?
Well, that's right.
How is the copper supposed to make air?
Magic, dude.
The magnesium.
I'm supposed to tell it.
I don't know how this is supposed to be. Someone else.
You wanna look at the examples over here?
Some of these are
This is like the reaction.
Oh, that's cool. That's the finished product.
inserts.
Yeah. We're gonna show other.
Carefully lower.
Open it, leave it in between.
That's not a bad idea.
Yeah, that's not a bad idea.
Yeah.
Max already said it, what's up here?
Like
So small.
yeah.
What's the metal
I can
that
try
melts?
opening
Can you
it
take
up a
your
little
finger on
bit. That way you can
Hold it for a long time.
Is it while we figure this out?
Yeah, probably.
And then we can leave it in between.
So are we ready to pause it?
Yes, I think so.
Okay.
I have the hydrochloric acid now. Yes.
So we want to have it intensive and then
Ah.
It's fine, I'll just drink the excess.
I wanna like show them what that looks like.
This is the
No,
magnesium.
you're not.
Oh,
There you go.
this is the magnesium in the tube that we're gonna add hydrochloric acid to. And it's gonna be a party.
Now, are you pouring the hydrochloric acid in right now?
We're trying to figure that out.
What's the hydrochloric acid reacting with?
The
Do
magnesium.
we want it to react yet?
No.
So take your guy out.
Okay. Oh ho ho ho. Oh ho ho. Thank you.
There you go.
Then we pour this on.
Okay.
Okay, don't touch it, Carly. It will hurt you.
I called dibs on,
Oh my god.
Okay. Okay.
So now that we put that in, fill this with distilled water. Yes, but don't mix the acid in the water. How do we measure that? Okay, so you just work slowly.
There we go. Start it.
How much distilled water are you putting in?
Until it reaches the top.
Yep, so you're gonna flip it, put your finger under the water.
Cool.
So I would make like even so that you can how much space that air bubble's taking up, because that's not actual hydrogen.
Okay, now slowly take it out of the position. Into the vertical position.
Now watch this, this is really cool. So look carefully.
This is really entertaining. You
Even
should
though
sing
they're
a song,
both
guys.
What song?
I don't know.
It's a final
Are we videoing like how we had the ice or the acid
First
Something that popped into my head was
Did we?
I'll give you a
I think we
hand
filled
if you want to like clamp it up so you don't have to hold it.
totally looks like there's a blender in the ceiling.
It
Random
does.
facts from me. Said work slowly, but my hand hurts.
Did I give you guys a clamp?
A clean? No. Okay. Cool.
What's the clamp for?
It's the whole this up and down.
Okay.
All the
Oh, yeah.
The other groups are making weird noises. Okay. We filled this entire thing with distilled water. The bottom of it has hydrochloric acid in it, and we don't have the magnesium in yet. And so we're gonna move on to the next step.
We're gonna win the bubble race.
Okay.
This needs to be above so it might be coiled. What? Might be the copper.
This is coiled too tight.
Longer.
Okay.
So it doesn't, I think it should be long enough. It doesn't have to go all the way technically to the 50 line like it says. That should be fine. Yeah, as long as it doesn't fall out. That's the biggest thing.
Yeah, we like smashed it in there. So.
Yeah, I think it should be okay.
And then just whoop.
Yep. Okay. So.
Okay, I
Yeah, you
don't want to do
put
that part.
it in this, and then you'll have your finger over it, put your thumb on it, and then go on it.
And this is just to hold it upside down.
Clamp it.
But it needs to be a big finish shut, nothing.
Yeah.
Right there.
Your turn, you're up.
Do you wanna do it?
Yeah, do it.
The $50 baton.
It's gonna spill if I put it in.
Miller bubbles.
Probably filmed that.
So I'm supposed to.
So we're putting the copper cage and the magnesium and the
Do you wanna show
whatever
this?
that.
Okay, guys.
When I'm supposed to
Apparently the other team's on this.
There you go, Isaac. And then into the water.
Don't burn your finger.
And then remove your finger. Uh-oh.
It's falling. Let's finish. Let's see what
Your little guy's gonna fall off.
Well,
Put your finger back. Is your finger back on?
Yeah.
Okay, pull it back out. Flip it over. We got to keep that guy secure.
I'm so sad. My heart is broken.
It didn't work, guys.
Oh, stay-at-home students get to see your family.
Just like wrap that around your hook.
Oh, like on the outside? Yeah, I think that would work.
See if that will hold it in place.
Okay.
Get some electrical pitches.
I need this one for myself.
Let go.
Awesome. Are we bubbling yet?
Would have happened already. Yeah. This acid doesn't work.
We should do with Karen's it's like we get salty water.
Alright, we are making our magnesium stay so that way when we put it in the water, it won't fall out. Yeah. A little tricky. Yeah.
Sorry, I needed to push against the bottom.
You know how
Why are hurts like to move?
we have this camp thing without picking it. Inside
Seem like that's gonna help.
helmet so they can scratch their nose.
Should we pause it while we're...
It's going underwater.
Okay, we're good.
Yeah, just top it off.
Take two, guys.
You know have cape on it because it fell off. Yeah.
Okay, guys, this is take two.
Yeah, Isaac.
And then do a new day.
Yeah, it's kind of opposite. I think it's like lefty tighty, righty loosey. Otherwise,
It's righty tighty, lefty loosey.
Okay, there we go.
Should I see if I can take off
So you're good, Isaac. You can move your finger. It looks fine. Yep, just keep it under the water while you screw it on, Carly.
Yes, I did record the. Wait, no, we didn't record the. Okay, sounds like a plan.
Now what's cool is if you look really close at the tube, you can actually see the acid traveling down.
Oh my god.
Oh, yeah, you can.
Even though I'm sorry, people on the video, you may not be able to see that.
Yeah, no, it's like moving.
But it has like a weird like waviness to it.
Yeah.
Okay, it looks like when you have floaties in your eye, and that's like moving down. That's what it looks like.
Yeah.
Like they're clear, you can see through them, but like it's moving.
You want to get in a little closer, and then because as soon you'll know when the acid hits, because it will start to bubble. Oh yeah, it's starting to right now. Yep.
Okay, let's do it close up. Yeah.
Yeah, it's already zoomed in. Yeah, I can see it bubbling.
You are awesome. Not only did we start like we started like 10 minutes later.
be good.
We're gonna be chilling here for a while. Yeah.
We did one full trial before you guys
This is our second.
Okay, cool.
Okay, everybody. If I could have your attention up here, while we let our things bubble. Okay, the other thing we're gonna do today, because of just time's sake with the pre-lab video issues and so on and so forth, is the lab was gonna have you do this through twice, because obviously it's good to get 2 sets of data to compare. But being that I don't think we'll have time for 2 trials, we're just gonna share with lab groups to get different trials. What that means is on your answers for your post-lab, you should have 2 sets of calculations for each trial, so we can kind of compare maybe which trial is more accurate. Another key thing with labs that you should always is if you ever notice, like you know an error happened. Like for example, maybe you started with an air bubble up top or something, like before it even started going. Write those things down right away so that later when you analyze your results, you actually can like have like, oh, well, we saw this, this would probably be why. So on and so forth. Okay, so first step here is in this space up above everybody is mostly hydrogen gas, if you didn't have any air bubbles in there. But because of the water that's in the tube, a certain amount of water will evaporate in that space up above as well. So the first thing we got to do is figure out, okay, of that space, how much is hydrogen versus the mixture of them. So by the way, you can do these on the very back page of your lab. It's blank. There's more space there than within the lab. If you want to do your post-lab on that, just the very last page. So the equation that we'll use is known as Dalton's law. This equation is on your formula sheet, but it's the idea that pressures are additive. Okay, I give you all permission to take your goggles off if you want. Because we're not touching anything. And these tubes aren't going to explode on us, so. Boom. How's that green on the board with the not the greatest? A dark spot.
Yeah, we did too.
Yeah, I think it should become a
You guys are Chem or like
Yeah, that's it.
Oh, wow.
Oh, yeah. How much air did you guys have at the beginning?
Okay, so the equation here, everybody, sorry, back to front. Okay, is the combination of the hydrogen and the water will equal the total pressure. Pressure is just an added.
I didn't go there.
Okay.
I was.
All right, give me your attention.
No, I did not.
So for our data, now this is different, okay? You're going to want to write this down on your data table. So the pressure in our room today in Lehigh, Utah, let me double check, is, where did it go? Sorry, let me pull up my barometer. You'll need it for your data.
Is that the barometric?
Yes, the barometric pressure. Okay, in Lehigh, Utah today, we are at 636 millimeters of mercury. So you'll want that for like your calculations. That's the total pressure you would use. For our example's sake, it's telling us that the total pressure is 746. Okay? We're trying to find the pressure of the hydrogen. The water pressure is dependent upon the temperature of the water. So if you turn in your lab to page 3, there's a data table there that tells you the vapor pressure based on the temperature of your water. So for the pre-lab sake, it tells us the temperature was what? Oh, 22 degrees?
Yes.
So that means the water pressure is 19.8. For your lab, that's why you have a thermometer at your station, is you're going to measure the temperature of your water after it's done bubbling to figure out what that is. Okay? So the pressure of our hydrogen would be 726.2. Okay? Questions on the first step of finding the pressure? Yes, Harley.
Wait, where did you get to 19.8? Is that the temperature?
So you take the temperature, which in this case it told us was 22, and then on the data table it tells you the corresponding pressure.
Oh, okay.
Does that make sense?
Yes.
Yeah, good clarification. Okay, question 2 says, we're now going to use the combined gas law to calculate the corrected volume of hydrogen at standard temperature and pressure. So we're going to find this information for our conditions, but we want to know what would it be for hydrogen under standard conditions. Okay? Now the combined gas law is the one where we rearrange the ideal gas law. getting rid of the things that aren't changing. So what's not changing in our lab setting here?
The pressure.
So we're not changing moles, that's staying standard, and R never changes, right? Temperature is gonna change here, because we're comparing it to standard conditions and our lab's not at standard temperature. So what that means is our combined equation is the P1V1 over T1 equals P2V2 over T2, where you put all the variables you're keeping on one side and then set up a before and after. For this case, the P1 side is like our lab conditions. The P2 side are the standard conditions. Okay, so for our lab conditions, we just found the pressure of hydrogen. What was it? 720.2? It told us the temperature was 22 degrees Celsius. And it also told me the volume was 31.0. Now when you do your post-lab calculation, this is the volume that you're finding right here. Right, that whatever that stops at, that's where you're measuring the volume, right? Because that's the way these are set up, is to measure the volume, the space that it takes up. Okay, standard conditions. Standard pressure is 760 in the unit of millimeters per mercury, by the way. You don't have to write this down, but this is equivalent to 1 ATM. So those two are the same. Okay. Standard temperature is 273 Kelvin. And then the standard volume is what we're trying to find. Okay? Questions on that setup? Yeah, Dan?
Well, I guess for the 22 Celsius, what's the number you add to it to get the Kelvin?
Oh, yes, so we will need to convert that, so it's 273.
Okay.
Yeah, good observation on that. That definitely has to be converted over. Any other questions on the setup? Okay, I'm gonna let you in a second practice solving that on your own or with your group. But I will tell you, just so you can make sure you're doing the pre-lab right, the answer you should get is 27.4.
Somebody write that down.
So you can write that down. Okay, our next step now, so now we know from that problem we'll find the volume. Now we need to compare that to how many moles were used. So the reason why, first off, just so you know, the reason why we calculated the grams of magnesium mathematically and not just setting it on a scale is because of how small a piece we're using. Our scales are not accurate to measure down to like the thousandths place. So it's more accurate to measure it by length and then do the conversion. So for this one, they said that they had a length or a mass of 0.028 grams of magnesium. What we want to know is how many moles of hydrogen that corresponds to. So our first step is to take our grams of magnesium, and we got to convert that into moles, because you can compare moles of one thing to moles of another thing. So someone remind us, how do I go from grams to moles? What do I use? Good, I gotta use the molar mass, which is like 24 something. 24.31. Okay, so first step is finding, well, how many moles of magnesium did we use? I got 0.0012. Then, to relate it to hydrogen, you compare it to, I'm going to bring back the equation that we looked at earlier. So in the equation, think of the equation like the recipe for the reaction. For every 1 magnesium that I used, it will make 1 H2. So in a sense, what we're saying is, okay, 1 mole of magnesium makes 1 mole of hydrogen. And so obviously mathematically it's just the same. So if you do everything perfect, that's how many moles of hydrogen gas you're making right now. If you didn't lose any or mess something up. About. Obviously your grams might be, has anyone calculated their grams yet?
Yeah, we did.
What did you get, just out of curiosity?
It's 0.02015.
Wait, it was.
It was 2015, I call it.
2015.
We got 0.018.
Okay, so yeah, so slightly, and it's going to be different because that's just the size of your magnesium, right? So, okay, questions on that step?
No.
So in a sense, with your lab, you'll just use your mass here to find out how many moles you made. Okay, the final step to get the molar volume is it's a ratio. We're going to do a ratio of liters per mole. So how many liters are made per mole used? So we know our moles. From part 2, or question 2, we found the milliliters. Milliliters to liters is just a divide by 1,000. It was 27.4 milliliters, which would be 0.0274 liters. So I'm taking liters. So this is from question 2. That's from question 3. Divide, and I got 23 liters per mole. What this tells me is that if I have a mole of hydrogen gas at standard conditions, it will occupy 23 liters of space. Now, this is an experimental value. The true literature value, if you want to write this down to compare later, is 22.4 liters per mole. So how well did they do on their lab?
Not that bad.
Yeah, they did pretty good, right? If this is the true, like, perfect value, I'd say that's pretty darn close. So that's kind of the goal, is you want to be as close to this as you can. Now keep in mind with any lab, if you go through all your calculations and you're not close, you don't go back and change things to make it close. That's lying.
What?
You just talk about in your analysis of maybe what caused the problem of why you did it not so great a job. So, any questions on that process though? So you'll go through like those same steps, but then with your data in the post-lab section. So, okay, how's our bubbling coming? We got 8 minutes. I'm doubting we're.